Hey folks, I'm Dr. Neil Spinner with Pine Research, and today I'm going to show you some of the exciting EIS circuit fitting and simulation features that our software platform, Aftermath Blue, has to offer. Now, for those of you who are existing users of a Pine Research potentiostat, let me first just say thank you very much. And if the model that you're using has EIS capabilities, for instance, the WaveDriver 100 or the WaveDriver 200, you already have access to these features at no additional charge. Your EIS capable potentiostat serves as the license for EIS circuit fitting and simulation features in Aftermath Blue for the lifetime of your potentiostat. However, if you don't own or currently plan to purchase a Pine Research potentiostat, software licenses are available for purchase separately. See the link in the description below to our website where you can view the license options available for purchase. Now, as researchers who collect and analyze EIS data know all too well, circuit fitting can be a very tricky and sometimes frustrating experience. And even though a lot of commercially available software programs have built in algorithms and calculation features, you may still find yourself getting stuck far more often than you'd like to admit. Or maybe you find that the user interface is just kind of clunky and hard to use, and it's just really too difficult to get that perfect circuit and that perfect fit. With Aftermath Blue from Pine Research, EIS circuit fitting and simulation has never been easier, and the user-friendly experience will make it your go-to application for EIS circuit fitting and simulation. So let's get started looking at the features that Aftermath Blue has to offer. But before we do, please remember to like this video and subscribe to our channel if you haven't already. And if you have a question, please feel free to leave it in the comment section below. So, as you can see here in Aftermath Blue, we use what's called an archive file structure. And what this means is that one file can contain multiple different elements. That includes things like experimental results, experimental parameters, notes, folders, plots, and of course, analysis tools like EIS circuit fitting and simulation nodes. Now, what this does is it enables you to have greater organization within the software as opposed to what you sometimes see with other software programs where there might be tons of files in all kinds of different locations on your PC or your external storage device. And sometimes finding the right files to have open at the same time when you're doing your analysis can be a little bit difficult. So when it comes to EIS data, if you've run the experiment using your Pine Research potentiostat, you might have a study node that looks something like this. Now, adding an EIS circuit fitting module to your data is as simple as clicking up here at the top. There's a circuit fit menu. And then from the submenu that comes, you click this option that says circuit fit. Or you can click over here at this icon that looks like a Nyquist plot and pick circuit fit from that submenu as well. If you're trying to perform EIS circuit fitting on data that you collected using a different manufacturer's potentiostat, you can import the data into Aftermath Blue from tabulated data. So for instance, here I have a 5-column EIS data set in a spreadsheet. However, for import into Aftermath Blue, you actually only need 3 columns of EIS data. And this is sometimes convenient in situations where the exported data from your other manufacturer's potentiostat only gives you 3 columns. So I can either pick, for instance, frequency and then Z real and Z imaginary, or I can pick frequency and the Z magnitude in the phase angle. And the software will automatically calculate the missing 2 columns in either case. In this situation, I'm going to copy all 5 columns because I have them all here. So I'm going to copy all 5 columns of my EIS data. Then in Aftermath Blue, I can come here to the top in the File menu, and I can select the Import External Data option. Alternatively, the keystroke Control-I opens the same dialog box. And in this dialog box, I'm first going to click over here on the drop-down next to Data Specialization, and I'm going to select EIS. Now, I'm going to right-click in the darkened region here in the middle and select Paste. And now you see the EIS data that I copied from my spreadsheet. All 5 columns are loaded in this dialog box. Another option is I could have clicked the Browse button here at the top and upload the data directly from the file, provided that it's in a CSV or comma-separated value file format. Now with my data loaded into the dialog box here, I'm going to click Import at the bottom right to complete the process. And so now, just like with the data that was collected using a Pine Research potentiostat, I have an imported EIS data set that can be analyzed by adding circuit fit module similarly to how I described before. When you add an EIS circuit fitting module in Aftermath Blue, the first thing that happens is the program is going to prompt you to pick an equivalent circuit. So there's several built-in equivalent circuit options that you can see here in the dialog box that opens up, and these include some of the more commonly used models that you might see, for instance, in the electrochemical literature. To select one, you can simply double click on it in this list, or you can click on it to select it and then click OK here at the bottom right of the dialog box. Another option is that you can draw your own custom equivalent circuit if you prefer, and that it can be close or even identical to one of the built-in ones. You can still draw it yourself if you like. So to do that, you're going to click down here in the lower left where it says New Custom Circuit. And that's going to open the designer window here. And so with this designer window now, you can see the circuit elements over on the right. We're going to drag and drop whatever circuit elements that you want to include in your circuit into this window. And then once all the circuit elements are there, you simply connect the left and the right nodes of everything. And that includes these in and out positions, as well as all of the circuit elements. And this will help you build and finish connecting the circuit to your liking. Another thing that you can do is that you can double click on any of the circuit element names to change them if you'd like. So for instance, in this case, I like to maintain the same number for resistors and capacitors or CPEs when I make a Voigt element or a Randall's element. So what I'm going to do is change this CPE name to Q2 so that it matches the resistor and it's a little more consistent. Now give this custom circuit a name, whatever you like, and then click the Save button and close the builder window. So now you see that this custom drawn circuit has an entry in the list. You can also add any notes to the circuit if you want in this area here. And then whenever you're ready, you can click the OK button in the dialog box to start fitting your data with your custom equivalent circuit. So within the EIS circuit fitting module in Aftermath Blue, you have a ton of different tools that are available to you, including things like fitting methods and weighting options. Now, the standard set of conditions for a newly added EIS circuit fitting module are a modified version of what's known as the Levenberg-Marquardt or LM fitting method, along with parametric weighting. But these can be changed at any time you want using both of these drop-down menus. So for the fitting methods, there are 3 available that can be toggled to be the active method at any time. And so that includes the modified LM, which I just mentioned, as well as the simplex and Powell methods. And for the weighting options, there's 2 primary choices. We have parametric and unity, though there is a third choice here called custom that's available. It basically enables you to modify the weighting on an individual point-by-point basis. But in reality, this option is somewhat relatively rarely used compared with parametric and unity weighting options. Now, having all of these fitting methods and weighting options toggleable from both of these drop-down menus at any time makes Aftermath Blue EIS circuit fitting extremely versatile. And in some other software programs, you only have the ability to select a single fitting algorithm or weighting option for the whole fit. And so with these other software programs, very often the ability to adjust either of those on the fly just doesn't exist. So the benefit of having that kind of toggleable feature available in Aftermath Blue is that certain data sets are going to look better, for instance, with something like parametric weighting and the modified LM method, while others might happen to look better when you do simplex and unity weighting. And so a more in-depth analysis of why certain EIS data sets behave better using certain fitting options or weighting methods is beyond the scope of this video. Suffice it to say that in many instances, you don't really actually need to know why one option is better than the other, but it's just helpful to be able to have all of these available to you so that you can test them all out experimentally and then eventually settle on the combination that gives you the best looking circuit fit in the end. A wide variety of tools are available to assist you when, for instance, the software doesn't instantly get the correct fit right after you've selected and applied your equivalent circuit. So in this particular instance, you can see an EIS data set where I clearly want to fit 2 semicircles or 2 Voigt elements, but the software did not immediately get it right. So you can see the full list of fitted parameters down here on the bottom right part of the screen. And next to each parameter, there's a box with a plus sign just to the left of each of these parameters. And these reveal the minimum and maximum allowed values during the iteration for that specific parameter. Now, every unit type, whether it's a resistor, a capacitor, a CPE constant, or an alpha, they all have their own default min and max values that are programmed into the software to limit the range that the algorithm can iterate. And it also captures what is likely the majority of the fitted values for most typical electrochemical systems. But of course, that might not be the situation in the case of everybody's data. So these can be changed easily anytime when necessary by typing in or choosing the value that you wish for the min and the max. A lock button next to each parameter here allows you to set a specific value and then prevent the algorithm from iterating on it. Now, the software is going to automatically iterate on any values that aren't locked, which by default is all of them initially, but you can toggle the lock status for any parameters as you need to whenever necessary. Now, changing parameter values can be done in one of a couple of different ways. So you can very simply type in whatever value you want into any of these boxes. You can also change the units of any of the parameter values that you wish using these drop down menus. And when you change the units, you very often change the parameter by, a few orders of magnitude at a time. But by far, the most popular method for changing parameter values is to simply drag these slider bars around. And most people find that these slider bars are really useful for quickly observing how one particular parameter impacts graphically the circuit fit, which you can do by just sliding these bars back and forth and then watching how the Bode and the Nyquist plots above change. Now, the EIS circuit fitting module also acts like a little web browser with these back and forward arrows. So, for instance, if you mistakenly drag a slider bar like really far over here and it messes up your circuit fit, and you really just want to go back to where you had it before, all you have to do is simply click here on the back arrow and it restores the last known set of parameters. So this also works, for instance, if you perform a fitting calculation and it goes somewhere that you don't like, or the fit gets worse and you want to go back to the set of values you had before. You can click the back button to restore the previous set of parameter values. Now, the combination of these tools, along with the different fitting methods and weighting options, lets you narrow down the best possible circuit fit in nearly all situations. So here, for instance, what I'm going to do is I'm going to lock the alpha values of the both CPEs here, Q1 and Q2. I'm going to lock the CPE alphas at 1, and then I'm going to do a quick calculation. So next, I'm going to hit the plus button here, and I'm going to increase the maximum limit for the Q2 CPE, and then I'm going to recalculate. And now finally, I'm going to unlock both of these CPE alpha parameters and let it iterate on everything. And so when I calculate here, I get a pretty good looking result. But you can even see here that when I just change from the parametric to the unity weighting, the fit gets even better, which you can tell by following, for example, the contours up here in the Bode plot from before and after. Kramers-Kronig is a diagnostic tool that checks whether EIS data is considered valid or not. Now, there are 3 conditions that are required of impedance data for it to be considered technically valid. Those conditions are stability, causality, and linearity. And now, while it's not a technically binary yes no type of diagnostic, the Kramers-Kronig tool is useful because it gives you what you might consider to be the ideal or best possible fit of your data. So, for instance, if the Kramers-Kronig tools do not fit your data very well, or they fit poorly in certain areas, you should not attempt to fit the data with any equivalent circuit because it will never fit as well. And it is very possible that the data should be discarded or considered invalid. In some cases, the Kramers-Kronig results can be, unfortunately, a little bit ambiguous. So in Aftermath Blue here, for instance, while you're viewing an EIS dataset, you can click up at the top here in the circuit fit menu, and then select the Kramers-Kronig option to apply the diagnostic tool. Now, in this case, you can see, for instance, that the overall fit is pretty good, but when we zoom into a little bit of the mid to low frequency regions, you can see that it doesn't match quite as well, which could mean something like drift or other kinds of nonlinearity or instabilities is causing a little bit of this non valid kind of behavior at these mid to low frequencies. EIS data can be simulated in Aftermath Blue, even if you haven't yet collected any data or imported anything into the software. So here in Aftermath Blue, if you click on the Circuit Fit menu at the top, you can choose the Circuit Simulation option. And then that launches the EIS Circuit Simulation module. So you can pick or draw a custom circuit, just as you can with a regular EIS Circuit Fit. However, in this case, when it launches with the circuit that you've chosen, the module looks similar to Circuit Fit, but there's no fitted data. There's only simulated data. So there's no fitting algorithms or weighting options available. Now, in the circuit simulation, just as with the circuit fit, you can adjust the parameter values. You can also adjust the frequency range here with these min and max boxes that the simulation data will show. And this kind of simulated EIS data can be really helpful if you just need to see what a certain circuit looks like graphically for a variety of different parameter values. And you can adjust those values to whatever you like and observe how the Bode and Nyquist plots change accordingly. A variety of error statistics are provided by Aftermath Blue when you perform EIS circuit fitting. So here you can see a data set that I have, and I'm going to add a circuit fit, and I'm going to fit this using the standard Randall circuit. So my values come up here, and what I'm going to do is I'm going to adjust some of the parameter ranges for these two CPE values in particular. And once I do that, I'm going to get a decent looking starting fit using the default options of the modified Levenberg-Marquardt and parametric weighting. So with this fit completed, I'm going to click on the results tab to reveal the error statistics. And this includes the chi-squared error statistic value, as well as the fitted parameter values along with their plus or minus confidence intervals. Now, very often, the strategy with EIS circuit fitting is to try to minimize this chi-squared error statistic. And sometimes that's with respect to picking different equivalent circuits and finding the one that gives you the lowest chi-squared error statistic, which would be an indication that that equivalent circuit is the most appropriate one for your data. On the other hand, you can also, within the same circuit fit, across multiple different settings, things like the fitting method and the weighting options, you can adjust those parameters to try to minimize your chi-squared error statistic. So for instance, in this case, you can see here the chi-squared value, which was for the default options of the modified Levenberg-Marquardt and parametric weighting options. Now what I can do is click back to the fitting tab here and make one simple change to go from parametric to unity weighting, and I'm going to recalculate. And you can see in this instance, the fit gets noticeably better. In particular, you can see the change in the Bode plot and the phase angle contours. And then I click back to the results tab here. You can see that that visual change is backed up by a new chi-squared value that's lower than it was before. Now, if the full set of results along with the error statistics are needed outside of Aftermath Blue, you can use this button here that says copy results to clipboard. So I can click this button and that copies all of these results in the error statistic, and it can be pasted into a spreadsheet for convenient viewing outside of Aftermath Blue. In some cases, an EIS dataset may contain points that we would classify as outliers. This could be things like drift or noise that shows up sometimes at low frequency. Could also be things like some odd effects that happen at high frequency that we sometimes call instrument artifacts that are usually the result of the reference electrode. In either case, hopefully as scientists and researchers, we can all agree that modifying or deleting scientific data is deeply unethical, and Aftermath Blue does not permit you to do this. However, we do have a feature in Aftermath Blue called dynamic point selection that allows you to selectively exclude or include points as needed from your circuit fit analysis. And this can help you achieve a really accurate circuit fit. So in this data set here, you can see what looks like a very simple semicircle. And so I'm going to add a circuit fit here to see what results I get. Now, overall, it looks pretty good, especially when you look at the zoomed out Nyquist plot up here. But you'll notice that the high frequency points here in the Bode plot, and then when we zoom into that corresponding region on the Nyquist plot, you can see an example of what we would call these outlier points or this kind of high frequency instrument artifact. You can also click to the results tab here and notice this really high chi-squared error statistic, which shows that the circuit fit is being really negatively impacted by this outlier region. So what I really want to do is not to delete points, but to just exclude these outlier points from my circuit fit calculation. So to do this in Aftermath Blue, I'm going to click here to the measured data tab, and you can see all of the data points here. I'm going to highlight the rows of the data that I want to exclude from my circuit fit calculation. And I'm going to right click on these points. And from this menu that shows up, I'm going to select the exclude selected option. Now you can see that on these plots above here, the points that I've tried to exclude, these outlier points, they haven't been deleted, but they are grayed out, which indicates that they are no longer going to be part of any subsequent analysis in this circuit fit module. So I can always highlight these rows anytime I want, right click and select to include them back if I wish to re-include them in my analysis. But for now, I'm going to click back to the fitting tab and I'm going to just recalculate this fit one last time. You can see that the fit visually changes only very slightly, but what we're doing is excluding these outlier points, and so they're no longer constraining the high frequency part of my data. And now I can click back to the results tab and see the new chi-squared value, which is much, much lower than it was before we applied the dynamic point selection method. EIS circuit fitting from Pine Research is available in two license options, Basic and Research. All of the features that I've shown to this point in the video are available in both the Basic and Research options. But note that all of the features from this point of the video on are available in only the Research option. A transmission line is a specialized equivalent circuit model that is sometimes used to represent porous electrodes. Now, in its construction, a transmission line consists of an infinite series sum of circuit elements, things like resistors, capacitors, CPEs, or a combination of these elements. And it's meant to capture the distribution of properties within the pores of an electrode. So this includes the electrode itself, the electrolyte, or the interface between the two. So in Aftermath Blue, there's a special circuit fit module for transmission line fitting. So up here in the circuit fit menu at the top, you can select the transmission line option to add this module to the EIS data. Now, unlike with normal EIS circuit fitting, there's no dialog box to pick your circuit, but rather in this case, the generalized transmission line model appears here. So by default, there's a leading resistor and a leading inductor, and each element in the transmission line is either a resistor, which you can see here with the X1 and X2 positions, or an RQ void element, which you can see are the default elements for the boundary positions ZA and ZB, as well as the middle element Y. Now, there's also two presets that are built in that you can select from the drop down here, which are called the B-scare open and the B-scare short. These are named after the brilliant and famous electrochemist Juan B-scare, who has published extensively on the transmission line model. So you can also choose the default option, which has all of the elements in it, and begin fitting your transmission line model to your data. And then you can later toggle back and forth anytime you need to between the fitting and the circuit tabs, and you can adjust the model, come back to the fitting tab, and continue to iterate on your transmission line and readjust your fit as necessary. If you have multiple EIS data sets that you need to perform circuit fitting on at the same time, you can use what's called the MultiFit batch circuit fitting feature here in Aftermath Blue. So in this particular example, you can see I have 12 total EIS data sets, and they're each labeled with a different potential at which that particular data set was collected. So the MultiFit feature is convenient in situations like this, where, for instance, I have a system and I change the applied potential slightly across a certain range, and the overall fit appears roughly the same, but the parameter values are changing slightly. And so you can see this trend, for instance, if I click here to the Nyquist plots all overlaid together, you can see that the trend in the equivalent circuit for all of these different data sets is the same, but they're changing ever so slightly with the parameter values across the potential range. So to do this, first, I'm going to add a circuit fit to one of the data sets. And I'm going to choose two void elements with a leading resistor to fit to my data here. So now what I want to do is apply this across all of the other data sets. So to use this multi-fit operation and save myself some time, I'm going to right click on the circuit fit that I just made, and I'm going to choose the multi-fit option here from the menu. Now, in the dialog box that pops up here, I'm going to check all the boxes of the remaining potentials that are in this folder here, and I'm going to click apply. That's it. I have just applied simultaneously the circuit fit, the same one, to all of the remaining potentials in this folder. And so I can click through each of these individual EIS data sets and see all of their individual fitted results. And this allows me to collect all the different parameter results and all the fitted values and observe the trends in the fitted parameters. All right, folks, that's going to do it for this video showing you the EIS circuit fitting and simulation features in Aftermath Blue. If you've got a question, you can leave it in the comments section below, or you can contact us at Pine Research directly. We'll see you in the next one.